Okay, good morning. Today is Monday, March 17, 2025. This is General Chemistry 1, Section 35, Spring 2024-2025 semester, and the time is 9:10 a.m. We are still in chapter number 6. We finished slide number 29. Okay, so that was the slide number 29. We're going to move to slide number 20 or 30. Slide number 30. But before I go through, I'm going to explain something and then I go through the slide as usual. Last time, I think I mentioned the specific heat, yes? Okay, and we say that the specific heat, okay, the specific heat is the amount of heat needed to raise the temperature of 1 gram of anything, of any substance by 1 degree Celsius, all right? Now, let me go through it in here, and here let me start with the specific heat, right? And we say it is actually, it is the amount, AMT, yani amount. I'm going to use abbreviation today, okay? Amount of heat or amount of energy that is needed to raise the temperature of 1 gram of a substance by 1 degree Celsius, okay? So we have the amount of 1 gram, and that's the amount of heat or amount of calories in here, okay? So that's this is the definition of a specific heat, which means in here, if I look at the specific heat, definitely it will have a certain unit, and the unit will be, for example, calories per gram per degree Celsius. Or we can say, if you want, joule per gram per degree Celsius, because the amount of heat can be expressed as joule or as calories, all right? Okay. Now, that's a specific heat. The other term I'm going to talk about is the heat capacity. That's another term in here. And the other term, I will call it heat capacity. Heat capacity, all right? And heat capacity, in the textbook, they give it a symbol. Specific heat, they give it a symbol. I'm not going to give symbols. I write it as specific heat. I write it as heat capacity. Now, heat capacity in here, heat capacity. What is the heat capacity? Capacity means بيستوعب, how much we can take. Heat capacity, it depends on what. Yani if I have a big guy and I have a small kid standing outside under the sun, whose temperature is going to rise faster, do you think? Who will absorb more energy? The big guy or the small guy? Okay. Who will absorb more energy from the sun? Who can withstand the weather more? A kid? Huh? The kid can stay longer than the big guy? The big guy can stay longer. Okay. Why? Because his mass is higher. Yeah. And it has high capacity. He can take more heat than the others. A kid cannot take as much heat as the adult can take it. صح? A kid cannot stay outside in the sun. Maybe can stay for half an hour, but an adult can stay for maybe 5 hours on the sun. Yeah, working in the sun. Yani, the heat capacity depends on what? Depends on the mass. Yani, now another thing that you have to memorize. So that's one thing you have to memorize. The other thing you have to memorize is that the heat capacity is equal to specific heat multiplied by mass. As simple as this. Specific heat multiplied by mass. Type. Now, specific heat, the unit is, let's say, calories per gram per degree Celsius. Huh? The mass, it is in grams, yeah? Now, when I look in here, gram and gram will get cancelled, and eventually, the unit of the specific heat will be calories per degree Celsius. Is this clear? Yeah? All right? Very simple, okay? Now, that's another thing you have to memorize. So I said the specific heat, the heat capacity is the specific heat multiplied by the mass. And a third thing that you have to go through in here is very important, and that's the heat absorbed, heat that is being absorbed, or the heat that is being released. Heat absorbed or heat released. Should heat absorbed, heat released? Remember, you have actually exothermic or endothermic reaction. Now, the heat absorbed or released, I will give it a symbol of Q. Could be calories, could be joules, could be anything. Now, and the Q in here, and you have to memorize this equation, is always equal to the specific heat multiplied by mass multiplied by delta T. Okay, so that's the Q in there. Now, if I want to play a little bit with this equation, now specific heat, the unit here is calories per gram per degree Celsius. Multiplied by mass, it is in grams. Multiplied by delta T will be in degrees Celsius. All right, now when I look in there, gram and gram will get cancelled, huh? Yeah? And degrees Celsius and degrees Celsius will also get cancelled, and that's why the Q in here, in this particular case, is going to be in calories, finished, all right? So that's the Q. These are the three equations you have to keep in mind in this chapter completely, all right? You don't need more to memorize. Now, if I want to play a little bit with this Q in there, can I move further? Yeah? Okay. Now, what we said Q is equal to specific heat multiplied by mass multiplied by delta T. Now, what I know in here, I know that the specific heat multiplied by mass, this is what? That's heat capacity, huh? Heat capacity, which means in here, Q, the charge, will be equal to heat capacity multiplied by delta T. So which one we want to use, it's up to us which one we're going to use. Is it all right? Okay. Yeah. Okay, good. Now, I gave you everything so far, but I'm going to go now through the slides. Talking about specific heat, we say specific heat, as I remember I said last time, specific heat is the amount of heat needed to raise the temperature of 1 gram of any substance by 1 degree Celsius. All right, that's what I said in there. And also, if you remember, I said also that if I take 1 gram of water, okay, 1 gram of pure water, and I stick a thermometer in here, and I'm going to put a stirrer in there. I want to stir the water in there. And I said, if you remember, 1 gram is 1 milliliter, and 1 milliliter is about 20 drops. You remember this, I said? Okay, good. Now, if I'm going to start heating, getting a source of heat in there. Now, right, I'm having some heat. Now, the heat should go inside. Since there is stirrer in here, the heat will be perfectly distributed everywhere. Now, what I have, before I add anything, I have a T1, for example, let's say 24 degrees Celsius, as an example. All I do in here is just look at the thermometer and heat it in there, stir it all the time. Now the temperature is going to rise. It's going to go up and up and up whenever I'm reaching T2. And if the T2 is exactly 25 degrees Celsius, now it means up to this point in here, the solution, the 1 gram of water has absorbed how many calories? 1 calorie. Okay, that means in here, what I'm having in here, there is only 1 calorie only. All right, because this calorie increase the temperature of 1 gram of water by 1 degree Celsius. Is it okay? Okay, clear? And then we can say, now, this is the specific heat of what? That's a specific heat of what? Of water. That's a specific heat of water. And then, by definition, the specific heat of water is 1 calorie per gram per degree Celsius. So that's a specific heat of the water. And that's by definition, okay? By definition is specific heat of the water is 1 calories per gram per degree Celsius, all right? Now, if I go in there, and that's the definition of 1 calorie. And if somebody will ask me, what is the 1 calorie? I would say 1 calorie is the amount of heat that is needed to raise the temperature of 1 gram of pure water by 1 degree Celsius. The definition of the calorie. Now we know the definition of the calorie. Now, if I go through this table will give you okay, it will give you the specific heat of several substances. Now, if you look in there, the water, look at the water in here. It is 0 point whatsoever. So that's actually in joule per gram per degree Celsius, remember. But in calories per gram per degree Celsius, it is equal to how much? 1 calorie per gram. Now, in joule, it will be equal to whatsoever. Okay, so that's the specific heat for the water. If you look for anything else in here as a specific heat, what you can see. Now, the Fe will have different, every material has got different specific heat. But what do you think? The water, okay, if I'm having, for example, water, okay, there is water and there is steel. I take the water, I take the steel, I put them down. The temperature is 24 in this room. Yeah. I take them, I put them outside. Outside is actually hot. Let's say the temperature is 30. Okay. Who's gonna be heated up quickly? The steel. Why? Yes, the specific heat is less than the water. Yani it takes a little bit amount of heat it will absorb, and its temperature will go higher quickly. But at the end, if I put a piece of steel and a piece or a certain amount of water outside, after sometimes both will have a temperature of 30 degrees. Okay, but some of them will get faster. Okay, they will go faster than the other, higher than the other. Now in here, this is what I say, it is heat capacity. They give it a symbol C. Will be equal to specific heat multiplied by the mass, S times M. And Q is the heat absorbed or released, is equal to specific heat multiplied by mass multiplied by delta T. Is that what we said? And also, specific heat multiplied by mass, it is equal to heat capacity. Remember this? That means the Q will be equal to heat capacity times delta T, where the delta T is the final temperature minus the initial temperature. That's the delta T. Okay? Final minus initial temperature. Now, okay, so that's regarding the specific heat. Now, the fire brigade, you know the fire brigade? يعني رجال الأطفاء. If there is any fire, what they do? They use what? Water. Why they use water? To turn down the fire. Why? The specific heat is very high. That means the water, when it comes to the flame, you know what's the fire? How the fire happens? Okay. If I want to make a fire, do I need matches? Do I need lighter? Can I actually set a fire on this paper without matches, without lighters? Not possible? Are you sure? Yeah. How can you burn it without flame?
Need other things, friction.
Exactly. Okay. Now, if I'm having any material, let's say I'm having a material, just for your information, all right? Now, how things will burn, how fire we get the fire. Now, if I'm having, for example, a certain material at a certain temperature, room temperature, let's say 25 degrees Celsius, that's a piece of material, okay? That's a piece of bread, let's say. It's a material, all right? Now, if I'm going to increase the temperature, I don't have to get a flame. Maybe I take a piece of bread, I put it in the oven, or I want to make cake. I put them in the oven, and then what will happen? Maybe I forget about them. What will happen? The cake is going to cook, and therefore, and after that, if I leave it longer inside the oven, it's going to actually, all the water will come out. And then it becomes dry, and then it will be more dry and more dry, and then it's going to start actually being very solid, and later on is going to change into black color, and suddenly it will, a flame will come out from there. And if I am not careful, the whole kitchen will be burned and the whole house might be burned. Okay, but the oven, it's not a flame oven, maybe an electrical oven, yes? So, and did not give a flame. You understand? So what will happen in here? There is something which is called a flash point. Flash point. Surely flash point. Flash point is a temperature of anything. Yani, the wood has got a flash point. My skin has got flash point. Everything has got a flash point. It's a temperature at which when the temperature of this substance is reached, so what will happen in here? It will start burning, yeah? That's the flash point. Now, if the temperature is going to increase and increase and increase and reaching the flash point, now a flame is going to appear in there. There will be a flame. Now, where is this a flame? That means the piece of material I'm having in here, it will have a flame. Let's say the flame is right in here, it start burning in here. Once it start burning at one point, then because now the other area will start absorbing the heat. It means in here the temperature also will get higher, and therefore will be another flame, and the temperature keeps on going and going and going. And if a house is burning, the temperature might go to 1,600 degrees Celsius. Okay. 1,600 degrees Celsius, that means the aluminum will get melted, everything will get deformed, metal will be deformed, and so on. What they do in this case, the fire brigade, in order to put down the fire, what they have to do, they have to spray some water. Now they spray the water in here, it's a high temperature, so what will happen to the water? The water goes in there, gets in there, absorbs the heat, the temperature of the water starts going up and up and up and up. When the temperature of the water reaching 100 degrees Celsius, it will start leaving the area, yani evaporating. That's beautiful. That means you put something in there, you take the heat and you throw it away in the sky. You understand? So what will happen in here? The temperature, when you put the water, the temperature supposed to come down, yes? So the temperature in here is supposed to go down because the water is being evaporated in there and taken with it the heat. Now, once the temperature is going to reach exactly the flash point, still burning, but when it's going to be slightly below the flash point, now there will be no flame. You understand what I'm doing? Yes? There will be no flame. Okay? Now, and that's when you put down the fire, okay, using the water, because the water absorbed the energy, went away, another water came and took the energy and actually took away the heat and so on. The energy is being taken out, okay. But there is a problem in here, and that was the problem with the fire brigade, just for information. The fire brigade and Rijal Atfa, when there is a fire, they used to go with a tank of water, and they used to fight the fire. They fight the fire, and now the fire is off. Okay, They don't have any more tanks of water because they use all the water. So what they do at that time, long time ago, they used to start their car and they go back to their station. By the time they go back to the station, what will happen? It will happen that a piece of wood, let's say it's been turned off, but now the heat here is high. The heat is high. Now the heat will go actually from place to place. Once the heat is going to one place, more heat coming to one place, this will increase temperature higher, and then a new flame will occur. Where are the fire brigade? They are back in the station. Now there is a fire, they will call the fire brigade, but it's too late because by the time to come back, by the time to fill their tanks with water, the building is actually gone. Now today, the regulation for fire brigades, if you know somebody from the fire brigade in your family or friends, any time when there is a fire, there should be, the fire brigade should be in their tank with water, many tanks, a car of their captain, okay, alone. That's another one. That means he will control how they're going to fight the fire. Police car will be in there to investigate. Ambulance will be in there at the same time. And when the fire is off, they cannot go anywhere. They have to stay there. And by this time, another tank will come with full of water, waiting. And if anything is happening, they have to sit down, having their mobile, sending jokes, whatever, half coffee, whatever, but they have to be in the scene all the time. They cannot leave until several hours. Once it is perfectly known that it is dead, then they can go back to the station, all right? So that's why we use the water in here, because it is cheap. Now, let's move to another thing in there. Now this is an example. A whatever grams of water, now I'm having the mass, huh? They give me the mass. Mass of water is heated from whatever to whatever. So that's a T1 and that's a T2. And from this, I can get the delta T. Am I right? So T2 minus T1, delta T. Calculate the amount of heat. Calculate the amount of heat. That means he wants me to find the Q in kilojoules by the absorbed by the water. What I got in here? Q is equal to what? Yellow. Specific heat multiplied by mass multiplied by delta T. Do I know delta T? Yes. Do I know the mass? Yes. Do I know the specific heat? We talk about water. The specific heat of the water is 1 calorie per gram per degree Celsius. If I want to change it to joule, how much will be? 4.18. Remember in here that every 1 calorie is equal to 4.18 joules. So, now, specific heat for the water is going to be equal to 4.18 joule per gram per degree Celsius. Now I can get it from the table. And this one, it is in grams. And this one, it is in degrees Celsius. I have all the values. I have this value. And therefore, I can get the Q. Is this clear? Yeah. And it will be in joules. But he wants in kilojoules. So I divide the answer by 1,000. And then I get kilojoules. All right? Now, let's see what they have done in there. Q is equal to specific heat times mass times delta T. Specific heat is right in here. That's specific heat. Multiplied by mass, they give me the mass. Multiplied by delta T, and the answer is that much. If I divide by 1,000, this will give me kilojoules. Clear? Yeah? Okay. Now, the other thing I'm going to talk about is actually the constant volume calorimeter. شو يعني calorimeter? Calorimeter. Calorimeter or calorimetry. Calorimeter means what? Meter means what? Device. Voltmeter is a device that will measure the voltage. Calorimeter is a device that will measure the amount of calories absorbed or released from a system. Colorimeter is a device that will measure the intensity of color. Okay, and so on. Oh, right. Thermometer and so on. Now, calorimeter in here. What is the calorimeter? Constant volume calorimeter in here. Let me explain it to you in better way. All right. And I call this one, if I want to call this one, I will call it a bump calorimeter. bump calorimeter. I will try to draw it in there. My drawing is not perfect, but follow me, okay? Now, bump calorimeter. Now, the word bump means what? يعني bump. You know, the bump in the army or whatever. The bump, it means it's a certain device closed, perfectly closed. That's the bump, okay? And inside there will be some two chemicals. And when you open, you trigger, the one chemical reacts with the other chemical to produce a chemical reaction that is very fast and will give a huge amount of energy. And that's why explosion will take place. But in here, bump, we're not going to make bumps in here. Bump, that means something very tight, very closed, okay? That means it will not increase in volume, it will not decrease in volume, and that's why we call it bump. Calorimeter, that means we're going to measure, using this device, I'm going to measure the amount of energy released or the amount of energy absorbed in there. Look what I'm going to do, just follow the steps in here. Let's say I'm having a certain container, okay, which is made of a certain material, which we call it, let's call it styrofoam. You know what's a styrofoam? Yeah. Styrofoam, if you go and buy coffee, they will give you a cup of styrofoam so you don't burn your fingers, okay? That's a styrofoam. That means it is an insulator. Now, you have a styrofoam in here, which is an insulator container of insulator, having insulator in here. And right in there, I can put actually a stand in there, okay, a stand. And in here, I'm going to put actually a piece of, or container of a stainless steel, okay, stainless steel, SS, stainless steel, because it's conductive in here. And this one was styrofoam in there. And I'm going to put in there, look what I'm going to put in there. Let me make it a little bit bigger so I can put some material inside. Now you have the styrofoam right in here. Sorry, stainless steel right in here. And it has a cover, but what I'm going to put in there. From outside, okay, I'm going to put in there a certain pipe. It's a pipe in here, and in the pipe in there, I'm going to push in there some oxygen. I'm going to fill it with oxygen, but طبعا it's gonna be closed. But before that, let's say I take a piece of material. Let's say a piece of biscuit, okay? This is biscuit, a piece of biscuit, okay? I put a piece of biscuit of known mass. I know the mass of the biscuit, mass of biscuit. I know the mass of the biscuit. I put it inside. And then I close this container. Okay, I close this container. So this container is closed perfectly with the screws and bolts. It is perfectly closed. And at the same time, what I'm going to put in here, at the same time in here, I'm going to put a certain device in there, which is going to give some trigger device. It means it has actually a heating element. You know what's a heating element? If you have in your kitchen, your cooker in your kitchen, if it's a gas and you want to turn it on, you press a button. It goes tick, 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 yeah? It gives a spark, yeah? So this one is going to give a spark in there, all right? And we fill this one completely with water, okay? This is going to be completely filled with water. H2O. And then I put actually the lid on it. There is a lid in there, غطا, of styrofoam as well, right? And in there, I'm going to stick in there a thermometer. I'm going to stick a thermometer in the water. So that's the thermometer in here, okay? Now, when I stick a thermometer inside, what happens in here? Now, inside here, I'm having oxygen, صح ولا لا? Yeah? And I'm having a piece of biscuit of a certain mass. And I have the water. Do I know the volume of the water? Of course, I know it. Do I know the mass of the water? Of course, because density is equal to 1. That means the mass of the water, I know exactly how much is the mass of the water. صح? Do I know the first temperature? T1. Yes, I know T1. All right. Now look what I'm going to do. I'm going to start my experiment. Now, to start my experiment, first of all, I'm going to start actually make the connection in here. Once I make the connection, then there will be some spark. If there is any spark in there, there is oxygen, the piece of biscuit is going to start burning inside. The piece of biscuit start burning inside, it means it's going to give some heat. Because this is stainless steel, the heat will go outside, صح? But in here, what I forget to put in there, I have to put a mixer in there so that when the heat comes out, when the heat is coming out, now the heat is actually released from the piece of biscuit after burning and passing through the stainless steel towards the water. The water will absorb it. There is a stirrer. That means the water temperature inside is going to be uniform everywhere. More burning, more heat coming. More burning, more heat. But I'm not interested of what happens in there. I'm interested what the temperature is going to go. How high is going to go. Now the temperature keeps on going high, 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 high to a maximum, and then we start going down. Now this is the maximum. It's my T2, which I record. That's it. My experiment has done. My experiment is done. Finished. Yeah. Now, what I'm having in here, from these two in there, from this one and this one, I can get the delta T, صح? I know the mass. Now, I'm looking for what? The heat absorbed by the water or the heat released by the piece of biscuit? What do you think? It is the same, exactly. But I cannot see how much it is actually released in there by the biscuit. But I can see it how much absorbed by the water, صح? Now, then I would say in here, the Q absorbed by the water, will be equal to what? Specific heat of what? Of water, صح? Multiplied by the mass of what? Of the water, multiplied by delta T. Do I know each one in there? Specific heat, it's 1 calorie per gram per degree Celsius. Mass of the water, of course, I know the mass of the water. Since I know the volume, it means from here, I know the mass of the water is also known. So I can measure it. Yani when I put it there, I can take it, put it in a volume, in a graduated cylinder, and I measure the volume of the water. So now, delta T, yes, I know because that's my experimental work. Now, whatever I'm going to obtain, this will be the Q absorbed by the water, the heat absorbed by the water, which is the heat absorbed by who? Released by who? By the piece of biscuit. If the piece of biscuit is 1 gram, then I can tell you that there will be, if you eat 1 gram of this biscuit, okay, the 1 gram of the biscuit will produce that much calories, all right? And that's actually what we call it in here. You know, people who are on diet and they want to know how much calorie they're eating, there is a metabolism. When you eat the biscuit goes into your stomach, there is metabolism in there, and this will release some energy. The energy released is exactly in there, and that's device, which is the bomb calorimeter, is a device that is actually everywhere in every food manufacturer. Any food industry, they must have it in their lab. That means they take a piece of, let's say, sausage, a piece of cake, a piece of whatsoever, they put it in there and they find how many calories this is going to give, and they put it in there and they say how many calories per serving, per gram, per whatever, all right? So that's how, when you look and you buy anything from the shelves in the market, you look in there and they should tell you in there how many calories are coming out, yeah? How they don't know it? They knew it using this device, the bomb calorimeter. Is it clear? Okay. So now again, that's the bomb calorimeter. Now, طبعا, the drawing is much better than mine. ما هيك? Is it? أكيد? Say no. Mine is better. No, that's much better. Now, what you see in here, again, this is actually the container, which is stainless steel container. You put a piece of material. It could be a piece of meat or a piece of fish or a piece of whatever you want to eat. And then there will be actually a ignition wire in there. There will be oxygen actually inserted in there, closed perfectly well, immersed in a solution in water of a known volume and known mass in there, and everything is in actually insulator with the styrofoam or anything. And then all you have the stirrer in here, and you have the thermometer. All you have to do is just to see the delta T change with the thermometer. All you do in here, you actually make the spark. Once you make the spark, it will start burning. The heat coming out will go outside, and because of the stirrer is going to be uniform, and the T1 is going to go up to T2, and now I got the delta T, and I can start doing my calculation. Now, Q of the system, when you have a system in there, the Q of the system, the heat of the system, is the heat of the water plus the heat of the pump plus the heat of the reaction, if there is any reaction. Now, طبعا reaction is combustion in here. So the Q of the system should be equal to 0, so don't worry too much about it. But the most important in here is the Q absorbed by the water is equal to specific heat of the water times the mass of the water times delta T. Is this clear? Yeah. Now, again in here, or you can say, this is what? C bomb. This is what? Heat capacity, صح? So the Q is also equal to heat capacity of the bomb multiplied by delta T. Okay? And delta H, we don't have to worry too much about it. Is it clear? We can go now through anything else. A quantity of whatever naphthalene, whatever grams of naphthalene. So I know the mass in here. C10H8, a pungent smelling substance used in moth repellent. You know with the naphthalene where you use it, yeah? If you have a carpet and you want to keep the carpet from 1 year to other year, so you put some naphthalene in there, you clean it, put naphthalene, roll it, and put it somewhere, not in the bedrooms, طبعا, okay? Keep it away. Why naphthalene is very good? Naphthalene is very good because it is a solid, but it will not melt. It will go sublimation. Yani it will go completely into gas. Once it goes into gas, all the gases will go inside the small channels of the textile, of the carpet. If there is anything in there, they will go in there and they will kill it. And the carpet will stay longer and longer and longer. So that's the good thing about the naphthalene. Okay. It is moth repellent and was burnt in a constant volume calorimeter. Consequently, the temperature went from T1 to T2. What I can get from here immediately? I can get the delta T. I know the mass in here. If the heat capacity, now they give me the heat capacity, mission specific heat. If the heat capacity is equal to whatever kilojoules per degree Celsius, okay, calculate the heat of combustion of the naphthalene on a molar base. Yani tell me how much heat per mole. That's on molar base. You understand what's a molar base? And find the molar heat, that is, find molar heat of the combustion. Yani molar heat. Molar heat, that means the heat released when actually 1 mole is being burned. Molar heat. Now again, I'm having the heat capacity. That means Q in here will be heat capacity multiplied by delta T. Is this correct? Is this correct? Yes? Okay. Now, I know the heat capacity. I know delta T. Now I can get the Q. Now the Q, I got the Q in here. But he wants the Q per every 1 mole. But in here, since that's the mass, it means from the mass, I can say the number of moles of this one is equal to mass over molar mass. From this formula, I can obtain the molar mass, which is 10 times 12 plus 8 times 1. That's the molar mass. Take this grams and divide by molar mass, you will get the number of moles. And here I have the Q. Now, when I take the Q and I divide by number of moles, this will give me what it will give me in this case. This will give me whatever kilojoule for every 1 mole. صح? And that's what they want. You see these steps? Very simple steps. Just if you understand the problem, you know what you have in front of you, apply it, go step by step, and you get to wherever you want. Let's see what they have done in there. I don't care about the strategy. Let's go in there. And that's what we said. We said the Q is equal to heat capacity. That's the heat capacity. They give it to us multiplied by delta T. Yeah. And we got that much the Q in here. That. Now, again, the Q in there, if I take the Q, divide by this one, but this will be out of how many? This will be kilojoule per what? Per gram. They don't want kilojoule per gram. They want kilojoule per mole. Yes? So I had to divide by the number of moles, not the mass in there. But if they divide by the by the mass in here, then divide it again by the number of moles, so you convert the grams into moles. But you don't have to do this. Change to moles and divide the value by moles, and you get the correct value. And this will be the heat of combustion, the molar heat of combustion of naphthalene. Okay, so this will be the molar heat of combustion of naphthalene. Now, because released, everything exothermic. Anything exothermic, you have to get it as negative. That means coming out. Well, positive, it means that's by convention, mustalah. Okay. Okay. Now, look in there in the bomb calorimeter, the water, the Q of the water is positive or negative? طبعا positive, because the water absorbed the energy. From who? From the piece of biscuit. But the piece of biscuit released energy. That means the Q of the piece of biscuit is negative whatever kilojoule, and the Q of the water is positive of the same kilojoule. Yeah? Okay. Right. Now, you've got in here fuel value of food. طبعا the food is our fuel. صح? If we don't eat, we don't have energy, and that's why our parents told us always eat to have energy. صح? Okay, good. Fuel values of food and other substances. Now, if you take, for example, sugar, take sugar, burn it in the presence of oxygen, you will obtain CO2 plus H2O. These are the product of the combustion, and there will be what? It will be delta H equal to 2,801 kilojoule for every 1 mole of the sugar when you burn it. All right. And notice in here, it's negative. Negative means what? Heat is being released. And that's exactly what will happen when we eat the sugar, okay? Goes into our stomach, metabolism will take place, and this will give us some heat. And the heat, we're going to use it later on and store some of it. Now, every 1 calorie is 4.18 joule, all right? So we have to keep this in mind. But if I look at the unit now, be very careful in here. If I say 1 kilocalories is equal to how many calories? 1,000 calories, صح? But 1 kilocalorie is equal also, they made it a new unit with a calorie with a capital C. Can you see here? It's a capital C, and in there a small c, صح? Yani from now on, if you hear somebody saying 1 calorie with a capital C, it's equal to 1,000 calories with a small c, yeah? Or it is equal to 1 kilo calorie with a small c. Is this clear? This is a new unit that was invented by the food industry people. 1 kilocalorie. Anybody? Okay. If somebody on diet, the doctor will tell him you can eat every day how many calories? Any idea? 20? 1,000 something calories? 1,000 something calories. All right. I don't know, but Thanks for telling me. Let's say 1,500 calories. A person who is on diet should not exceed this amount every day. Every day? I don't know. Let's, inshallah, okay. Now, when they go to the supermarket and you look for a certain device, let's say a certain device, a certain material you want to buy, you will see a lot of writing in here. Yes? Those people who are on diet, the first thing they look at the expiring date, and also they will look for the amount of energy, yeah, which is the calorie value. Now, in here, it will not tell in there, but it might tell 1.5 calories with a small c. 1.5. شو يعني 1.5? It's 1.5 kilocalories, يعني 1,500 calories. But the person who's reading this 1.5, this is 1.5. But I am allowed to have how many? 1,500. Sure, 1.5 compared to 1,000. It's nothing. By the time I take my trolley to the cashier to pay the money, I eat maybe half of this container. So then I pay for the rest. Then I get bigger and bigger. Then I have to go back to the doctor. Okay, you understand how it is? It's a trick, right? And why it's a trick? Because when it is on the on the can or anywhere, it's written in a small font. It is really capital, but you cannot see it's capital. For me, I can notice. Now for you, you can notice it, but for ordinary people, they don't notice it at all. They think a letter from the start of actually a word, you write it capital, so they wouldn't think this way. So that's the calories, and that's actually the fuel value of the under. Is it okay? Now again in here, when you go apple, for example, every 1 gram of apple will release 2 kilojoule. Every 1 gram of apple, 1 gram, nothing. Yes. Okay, and so on. You don't have to memorize anything in here, but you can tell from there. Always they are negative in there, so that means that's the amount of the heat that is going to be obtained. Now, this is, we call this one. So the first one, it was called bomb calorimeter. Yes, this is called bomb calorimeter. Another calorimeter in here, this is called the coffee cup calorimeter. Coffee cup calorimeter. Sure, coffee cup calorimeter. It speaks for itself. You know, when you buy coffee, they give it to you in a certain cup, and the cup is made of styrofoam, so you don't have to burn your fingers. Yeah. Now, coffee cup, that means if I have 1 cup in here, you can have 1 cup of styrofoam and another cup of the styrofoam. Now, take a pair of scissors in here and cut this one. If you cut one of them with a pair of scissors in there, cut one of them. Okay. Now, once you cut it, it's gonna be small. So now take the first one in there. That's the first one. Let's say that's the first one in here. Take the second one in here and put it, and then when you put it, it will go inside. Am I right? Yeah? And you cut one and you put inside the other. Now, this is made of styrofoam. That means, again, let me draw it in a better way. Now you have 1 cup, and there is actually a second cup in there. All right? There are the 2 cups. Styrofoam, that means the system is isolated. No heat will go out, no heat will come in. It is actually together. Now, what we can do in here, you can actually stick in there, because if you have a thermometer or a pen, you can push it inside, it goes easily. Yes? You can put a thermometer in here. That's a thermometer. And also you can put something that I'm going to, let's say the same thing as this one, a hook or whatever, and I'm going to keep on this one moving up and down. That means I'm going to stir the solution. And then what I'm going to have? I'm going to have, for example, acid. Okay, this amount of acid, I'm having acid in here, and I'm going to have a certain base, let's say, and this is a base in here. For example, HCl and NaOH. solution, HCl and NaOH. Take the HCl, pour it in there, keep it in there, measure the temperature, and this will give me the temperature T1. Yes? Now, second step in here, take the sodium hydroxide, put it inside. Now the sodium hydroxide goes inside, you stir it. Now reaction will take place because acid plus base will give me salt plus water plus energy. It will give me some energy. Now, because it's giving some energy, now the temperature is going to rise up to a maximum, and this will give me the T2, a maximum value. From T2 and T1, I can get the delta T, صحيح? Okay, now delta T, I can get it. Now, also, if I know the specific heat of the solution, now I need the specific heat, and I need the mass of the solution. I know how much grams of acid, how much grams of base. I add them together. This will be the mass of the total mass of the solution, multiplied by specific heat of the solution, multiplied by delta T, which is T2 minus T1. This will give me the amount of energy. So, now, this amount of energy, this will be actually, is this a constant pressure? Of course, it's not like a bomb. It's constant pressure because it will be some opening somewhere to the atmosphere. That means the pressure inside is equal to the atmospheric pressure. Okay, and this way we can calculate in there. So this is an insulator. No heat can enter and no heat can leave in there. So you have the thermometer, you have the reaction, for example, A plus B. This will give me some heat, and the temperature is going to go from T1 in here to maximum T2, and this way we got the temperature. We call it a coffee cup calorimeter. Of course, in here, this device in there, you can buy it. Maybe you pay $50 or maybe $100 for this piece. But if you make it at home, I think you have to make it in the lab sometimes in one of the experiments, if still in there. This will not cost you anything because you can get it free, the cups, okay? It might not cost more than half a dirham, all right? Okay. All right, now let's have a look in there and let's look at this example. A lead, okay, a lead pellet, you have a piece of lead, رصاص, lead pellet that has a mass of whatsoever. So we know the mass of this lead. We know the mass of this lead. We know. At whatever temperature, now the temperature was, that's the T of the lead, okay? T of the lead, يعني. It means the lead is being heated, صح? Because room temperature is 24, 25. Now the piece of lead is heated up, was placed in a constant pressure calorimeter of negligible heat capacity containing whatever milliliters of water. Now I'm having the mass of the water in here. Okay, there is water, and okay, the water temperature rose from 25. Yani I had water in there, so I had the water. There is H2O in here. And I know how much it is. It is 100 milliliter of water. Now I take the piece of lead, that's the PB, which is quite hot in there. The temperature is high. Now I'm going to put it inside. Well, the moment I put it inside, what will happen in here? Okay, the temperature of the water was 25.5 degrees Celsius. All right, so what will happen? The temperature of the lead was 89.98 degrees Celsius. Huh? Whenever I'm putting the piece of lead inside the water, so what will happen? The heat will come out. Now it means the temperature of the water is going to increase while the temperature of the lead is going to decrease. صح? The lead will lose heat and the water will absorb the heat until both temperature will be the same. Yani the final temperature of this one. So this one is going to drop down to how much? It will drop down to 23.17 degrees Celsius. And this temperature is going to go up to how much? كمان 23.17 degrees Celsius. Is this clear to both of you? Because at the end, both will have the same temperature. The piece of lead, his temperature will decrease, and the water temperature will increase until they are the same. Once they are the same, that's it, finished. All right. Now, what is the specific heat of the pellet? How much is the specific heat of the lead? We need to find the specific heat. If I want to find the specific heat, remember, specific heat is equal to heat is equal to specific heat multiplied by mass multiplied by delta T. I'm talking about specific heat of the lead. The Q released from the lead is equal to specific heat of the lead, and that's what we want to find. Multiplied by the mass of the lead, I know the mass, multiplied by delta T. Do I know the delta T of the lead? Yes, and the delta T will be positive or negative? Negative طبعا انه final temperature is low, higher initial temperature is high. Okay, now what I need this one. Do I know Q? I don't know the Q yet. I need to find the amount of energy released from the lead. Amount of energy released from the lead is equal to the amount of energy absorbed by the water. صح ولا؟ Okay. Now, Q absorbed by the water is equal to specific heat of the water multiplied by the mass of the water multiplied by delta T of the water. صح? Okay. Do I know the specific heat? Yes. Do I know the mass of the water? Did they give me the mass? That's 100 milliliter, which means it is how much? 100 grams. Okay. Multiplied by delta T. Delta T, it goes from where? It is 23.17 minus 25.5. And this will be the Q of the water. The Q of the water will have a sign. The Q of the lead will have opposite sign. To make them equal, that means the Q of the water will be equal to minus Q of the minus Q of the lead. All right. Now, once I know the Q in here multiplied by minus, now I know the Q of the lead. Once I know the Q of the lead, I know the mass of the lead, and I know the temperature change of the lead, now I can find the specific heat of the lead. Yes? Okay. Now, that's a strategy in here. We don't care about the strategy. Now, again, notice in here that the Q of the lead must be equal to minus the Q of the water and vice versa. Okay. Now, the heat of the water, as I said, Q of the water, the heat absorbed by the water is the specific heat of the water multiplied by the mass multiplied by delta T. Delta T is the T final minus T initial. Now, Q of the water is equal. This will be the mass, and this is the specific heat for the water, and this will be the delta T. Now we get actually the Q for the water. Now, the Q for the lead will be equal to negative. Okay, that's the Q for the lead in here. And the Q of the lead is also equal to specific heat multiplied by mass multiplied by delta T. Set everything in there. We don't know the specific heat, and that's what we need to find. And also notice in there we need actually to find the change in there in temperature. Notice in here this will be negative, صح? And this is negative. That means it's gonna be positive. مظبوط? At the end, okay, from here we can get the specific heat, and the specific heat is equal to 0.158 joules per gram, if you want. All right. Now, we have how many minutes? One more minute. Okay. Right. Let me finish. Okay. We leave this one, and we don't have too many slides. Okay. So next lecture we finished everything, inshallah. Okay, thank you. Can I have the attendance sheet, please?